Okay, so have you ever just typed a few words into an AI model and watched a breathtaking, photorealistic image materialize right before your eyes? I mean, it literally feels like sorcery, right? But behind the curtain, it's not magic. It's a series of incredibly precise mathematical steps. Welcome to This Explainer. Today, we are going deep behind the scenes to reveal the exact mechanical gears that make text-to-image generation possible. Let's dive right in. Here's our quick roadmap for today. We'll start with sculpting images from static, then check out the UNet engine, look at translating words to pixels using Clip, dive into steering the diffusion process, and finally explore what lies beyond the canvas. Take a look at this wild prompt. In an ornate historical hall, a massive tidal wave peaks and begins to crash, and two surfers, seizing the moment, skillfully navigate the wave. This exact text was used to generate an astoundingly realistic video by OpenAI's Sora. Now, what's absolutely fascinating here is, well, this event never happened in history, obviously. So there is literally zero chance this specific visual existed in the model's training data. The AI isn't just regurgitating what it's seen before, it's actually generating entirely new visuals from scratch. But how? How does it actually do that?
That brings us to Section 1, Sculpting Images from Static.
To teach a model to build an image out of pure static, we actually have to completely reverse the problem. First, we have to teach it how to destroy images. We call this the forward process. Basically, we take a perfectly clear image from our training data, and we incrementally add a layer of random mathematical noise to it, just static, until it becomes totally unrecognizable. By doing this over and over again, we create millions of these input-output training pairs. Then, the model learns the reverse process, taking a slightly noisy image, predicting the tiny amount of noise that was just added, and mathematically subtracting it to reveal a slightly clearer picture. Once the model learns how to do that, generating a brand new image goes a little something like this. Step 1, we start with a canvas of pure random noise. Step 2, the model predicts a tiny amount of noise within that static. Step 3, it subtracts that noise. And step 4, it loops this process anywhere from 50 to 1,000 times. And gradually, almost like magic, a beautiful image emerges from the fog. By the way, this incremental loop, that's exactly why tools like Midjourney make you wait several seconds for your image to actually render. Now, you might be wondering, why subtract the noise incrementally? Why not just jump straight from pure noise to the perfect image in one single go? Well, MIT's Professor Rama Ramakrishnan has this brilliant analogy. He says, you can't cross a ditch in 2 jumps. The gap between absolute static and a pristine high-resolution image is simply way too massive for the model to leap across all at once. It absolutely requires a bridge made of dozens or even hundreds of tiny, manageable baby steps. Okay, so we've got this conceptual loop of predicting and subtracting noise. But what is actually doing the heavy lifting here? What kind of engine can process these massive, complex pixel transformations over and over again? Let's look at Section 2, UNet, the processing engine. Enter the UNet. This is a U-shaped neural network architecture. Interestingly enough, it was originally created for medical imaging segmentation, like looking at MRI scans, but today it is the absolute powerhouse behind generative diffusion models. Its main job is to take an image, shrink it way down into deep numerical representations, and then expand it all the way back out into a final image. Let's break down how that architecture physically works. On the left side of the U, convolutional layers basically compress the image, shrinking its physical dimensions while making the data channels much, much deeper. Then, on the right side, up convolutions expand that deep, dense data back up to the original image size. But here is the real secret sauce: residual connections. Think of these as direct bridges. They pass the original high-resolution details from the left side directly to the later layers on the right side. This is absolutely crucial because without these connections, the model would compress the data so much that it would completely forget the fine details of the original image. Okay, so our UNet engine is incredibly good at crunching numerical pixels and subtracting noise. But here's the elephant in the room. If the engine only understands mathematical pixel arrays, how on earth do we ask it for, say, an astronaut riding a horse using everyday English text? That takes us to Section 3, Clip, translating words to pixels. So OpenAI created the Clip model to basically bridge text and images into one shared mathematical space, which we call an embedding space. They achieved this using what's known as a contrastive learning matrix. They feed the model an image and a text caption, right? And the model's sole job is to maximize the similarity scores for matching pairs, which you see as those high scores on the diagonal line, while simultaneously minimizing the scores for completely irrelevant pairs off the diagonal. It literally forces the mathematical representation of the word dog to sit right next to the mathematical representation of a picture of a dog. To make this actually work, the model needed an astronomical amount of data. 400 million image caption pairs, to be exact, all scraped directly from the internet. And here's a fun fact for you. Most of these captions actually came from the alt text hidden in website code. You know, those highly descriptive, verbose labels designed for accessibility. They turned out to be the perfect training data. Moving on to Section 4, Steering the Diffusion Process. Now we put it all together. Here is exactly how an image is generated step by step when you hit enter. Step 1. Your English text prompt is run through the clip model to create a mathematical embedding. Step 2. This text embedding is mathematically combined with a canvas of pure random noise. Step 3. Both of these are fed directly into the UNet. And Step 4. Because the text embedding lives in the exact same mathematical space as the images it describes, it effectively acts as a steering wheel. The UNet iteratively denoises the static, but it is constantly steered toward that specific text embedding until your requested image finally emerges. And this brings up a really cool point about how tools like Stable Diffusion revolutionize the whole space. Instead of running this extremely heavy denoising process on massive, full-resolution pixel canvases, they use a clever trick called latent diffusion. They compress the image into a much smaller embedding, do all of the iterative noise subtraction in that tiny latent space, and then expand it back into an image at the very end. This little shortcut is exactly why you can generate a masterpiece in seconds instead of waiting hours. And because this steering is purely mathematical, it gives us incredible precision. Take negative prompting, for example. Let's say you ask for a Labrador in the style of Vermeer. You get a gorgeous painting, but the dog is wearing a blue scarf. And, well, you hate blue. No problem. You simply add a negative prompt, blue. The model then mathematically subtracts the embedding for the color blue from the generation process. The result? You get the exact same beautiful painting, but with all the blue elements perfectly erased from the canvas. It's wild. Finally, Section 5, Beyond the Canvas. It is so vital to remember that despite how smart these models seem, generative AI has zero inherent domain knowledge. None. It doesn't know the anatomical rules of biology, and it certainly doesn't know the laws of gravity. It only knows statistical pixel patterns. This is exactly why you'll often see AI hilariously render humans with 5 or 6 fingers, or output a messy, jumbled distortion when you ask for something it hasn't seen together. Like an MIT professor riding a horse. It's just unconstrained statistical sampling. There is no actual physics or biology engine under the hood. Which leaves us with a really fascinating question for the future. Models like Sora are trained on massive amounts of sequential 2D frames. But when you see Sora generate a video where beach sand impossibly falls right through the solid seat of a chair, it sharply reminds us of its limits. So the big question is, will these models, simply by ingesting enough data, eventually learn the actual 3D laws of physics organically? Or are we really just building more and more spectacular illusions? It is an incredible frontier to watch. Thank you so much for joining me on this explainer. Keep learning and stay curious.